for putting this all together, and welcome everybody. It's wonderful to be in touch with you all. I obviously don't know you individually, but look, really it's that dialogue, that discussion going forward, and basically all your questions, and of course the attempts to answer them today, but also to follow up as key issues, key questions come up, that we can really respond to them. Bit of background, I'm a soil microbiologist. I've been doing work for the last 50 years, initially in research work, forest diseases, soil microbiology, the driving processes of these diseases, but then very much went into work with, again, CSIRO, tropical crops and pastures, looking at the nutrition and how do we use soil microbial ecologies to enhance the nutrition dynamics and colonization of degraded landscapes, arid landscapes. So had a long research history, basically in Australia, but also China and overseas. So very, very interesting. I spent a long time then working, and in a sense, how do we get this research applied practically, commercially, in innovation at a regional, industry and national level. But basically about 15 years ago, retired quite deliberately early, because I just wanted to get back onto grassroots, hands-on, catalytic activity with very, very innovative farmers in Australia. Formed a group called Healthy Soils Australia to do that, and then worked a long time with leading political strategies in Australia to get this whole land regeneration story done. Now this has grown bigger, and of course we now work under a group called Regenerate Earth, a little NGO, and basically it's this bigger issue of how do we take this regenerative story, this land management story, into that bigger global context. The context, of course, as we all know, we're really in it, is actually climate change, right? And so basically have come into this climate story from actually the solutions end, from how did nature initially create the climate, regulate the climate, what have we done to it, what can we do to actually now respect nature and bring back the balances and therefore naturally, safely cool the planet. Okay, so that's been the context. And basically when we look at climate change from this natural perspective, see, we get a completely different picture, and it's really explaining that picture, but also out of that picture, here are new solutions. You'll all recall basically 50 years ago, Charles Keeling basically put the evidence out there from Hawaii. Yes, CO2 was going up abnormally, dangerously, right? And so we had that clear rise that, okay, CO2 was going up. And definitely, without any question, CO2 is a greenhouse gas. It's a component of the global warming effect. And therefore, we had to think, okay, a gas is going up. It's a greenhouse gas. This spells danger. And what we did is we then looked at this as actually, okay, here's a causal problem, rather than seeing this as a symptom, right? CO2 was going up, absolutely, but was it the cause or was it a symptom? Were there bigger driving factors behind it? And of course, that's the difference. We've spent 50 years now totally focused on CO2, where the emissions, and of course, then we focus on our fossil fuel use. And so the whole debate has been, okay, how do we reduce emissions from fossil fuel use? And basically, that has been our context and our perspective on controlling global warming. And the tragedy is, of course, that CO2 is only a small part of this whole global dynamic, this global weather dynamic. It is actually water for the last 4 billion years that has controlled 95% of the heat dynamics of the blue planet. Now, this is really climatology 101. It's a starting lesson for climatology. It's water. And the CO2 component of the greenhouse effect governs about 3.84% of the heat dynamics of the blue planet. And yet we've fixated on this 4% and completely ignored the 95%. And of course, that has caused all sorts of distortions. The second thing, we've so focused on CO2 and its emission reductions, but really this is a real problem because physically, in terms of nature, we can't control CO2 like that. Okay, we've got about 750 billion tons of CO2 in the atmosphere, but we've got 38,000 billion tons of CO2 dissolved in the world's oceans. And as we remove CO2 from the atmosphere, the oceans will re-equilibrate CO2 back into the air. And so it will take hundreds, if not thousands of years of CO2 emission reductions to try and pull CO2 back to 300 parts per million rather than the 415 that it's at now. So physically, basically, it doesn't work. We can't stabilize CO2. We can't stabilize the climate through CO2 reductions alone because, one, it's only 3.8%, and secondly, it'll take thousands of years. The third thing is even more sort of limiting in a way, is because, okay, there's 7.5 billion of us on the planet at the moment, and all our ecologies and economies and social stability has really been founded on oil. Basically, we've been in this Ponzi scheme of oil substitution and really living on the free, easy energy from old solar energy stored in oil. And of course, if we took that oil energy away, quite frankly, most of our economic activity would collapse. And of course, there's no 7 billion people on this planet volunteering hari-kari. We can crash ourselves because that social, the social cost would be impossible. So we can't just turn off oil and turn off emissions from oil because the social economic thing is untenable. And so we've really got a situation that basically it's 3.8%. It's physically impossible in the time frame we've got, and it's economically and socially impossible because of the consequences. And so for the last 50 years, we've been stuck in this sort of black hole of impossibilities. And as we know, in December last year, we had the Madrid COP25, and it basically came to a conclusion, yeah, we can't do anything, or we don't agree to do anything. And in a sense, we've even walked backwards from the Paris COP21 agreement from 2015, where at least we had a vision of zero net carbon emissions, but we've walked back from that because it's just too difficult. There can't be this oxymoron of international consensus. Okay, and so we really are in a very serious situation because, one, after 50 years, we're not addressing the problem, but climate change, of course, hasn't stopped. Climate change has kept on going, and climate change is expressing itself now violently, dangerously, through hydrological extremes, whether it's cyclones, hurricanes, storms, floods, droughts, aridification, wildfires. It's actually hydrological extremes that have gone exponential, and it's hydrological extremes that are actually breaking down, killing people, breaking down biosystems. And as in Australia in the last 2 months, we're at this tipping point now with wildfires, where biosystems are actually being impacted and risk actually collapsing and moving rapidly back to desertification because of these hydrological climate extremes. So what I've been saying up to now is pretty depressing and damning, and the answer is no, you can't get there through that mindset. And so the question is, how do we change perhaps our mindsets, but more importantly, how do we look at nature and really the bigger context of what governs the Earth's climate? What have we done to it? What can we do to change it? And what change do we need to make to have an effect on that? And the good news, and so it's early in the morning here, but I want to come with the good news, is yes, look, we can naturally, safely cool the planet, rehydrate the planet, regenerate the planet, maintain social stability, feed the 10 billion people that we project will be on this planet by 2050. That's 30 years away. We can do all those things, but we have to change. We have to change and look at the world in a different, natural way compared to the way that we've done through this linear, very reductive CO2 climate, model. And it comes back to the simple thing of, okay, nature, how does it work? And as I said in the beginning, it sort of basically governs the climate. It governs 95% of the heat dynamics of the blue planet. And it's those heat dynamic processes, those hydrological processes, that in a sense regulate our climate. And it comes down very simply that, yes, if we can just go back to how nature created the climate, look at those processes, look at regenerating those processes, then we can rapidly cool the climate. Now, we can have a lot of discussion on each of the processes and steps involved, so I don't want to get into that now. But the bottom line is to say, well, what is the key strategic action point, the empowerment point for societies, grassroots societies everywhere? And that is very simple. And the take-home message is we need to regenerate the Earth's soil carbon sponge everywhere urgently. Okay, it's regenerating the Earth's soil carbon sponge. So instead of seeing CO2 as the bad guy, the cause, or instead of seeing it as a symptom, we've got to say, look, this is actually a resource that is increasing because nature isn't biosequestering as much of it as it used to. And nature used to take this carbon from the air and turn it into stable soil carbon to rebuild the Earth's soil carbon sponge. And of course, that sponge was able to infiltrate, retain water and make it slowly available for plant growth and extend the longevity of green plant growth across this planet. And it's actually that simple process that nature used terrestrially 420 million years ago to turn what was barren, dry, arid rock, and oceans, of course, but turn that barren, dry, arid rock into verdant, green, forested biosystems. And it did that by microbes solubilizing or growing onto that rock, solubilizing it, putting organic matter in between the mineral detritus. That organic matter started creating the sponge, its capacity to hold water, and from that rapidly we got then the evolution of pedogenesis of soils, but then of course also the vegetation that grew up very rapidly from lichens to mosses to ferns to cycads to gymnosperms, angiosperms, and of course basically very rapidly this pedogenous soil forming sponge processes enabled the whole 14 billion hectares of ice-free land on this planet to be then vegetated. And that vegetation then of course draws down the CO2 from the air, and of course it builds a hydrology and it builds the cooling because it's the hydrological processes that actually cool the planet. Simply matter, simple, one of the processes, it is just the transpiration of water from the soil, from the sponge, through trees and plants, taking that water back up into the atmosphere, converting that water from liquid to gas that takes 590 calories of heat energy for every gram of water that is transpired and evaporated. And that 590 calories of energy comes from the Earth's surface and of course cools the Earth's surface. So we've got actually here's nature's air conditioner, nature's cooling mechanism, where basically 590 calories of heat energy for every gram of water transpired goes into the atmosphere, and in doing so cools the surface. That effectively in nature, or not more, in nature was more, even now, that process of transpiration takes 24% of the incident solar radiation coming into the Earth and takes it back up into the upper atmosphere, and then from there largely out to space. Okay, that's 24% of the incident solar radiation is being cooled or is being returned to space through this process. We're at the moment working with less than half of the terrestrial green transpiring surface that nature had evolved and existed 8,000 years ago. So, you know, we have basically decimated half of the Earth's forest and green vegetation. We're operating with half of the natural air conditioning of this planet. And of course, by restoring some of that, we can actually safely, naturally cool the planet. It's again, very, very simple question. We get away from simple CO2 black holes or traps. Okay, global warming, what is it? Okay, very simple. We've got a planet, we've got a sun. The sun is releasing incident solar radiation continually out to space. The Earth at the top of the troposphere receives 342 watts per square meter of solar energy continually on average all over the Earth. So, okay, we've got a sphere, it's receiving so much energy coming in. To have a stable climate, it's fair enough that we need 342 watts of energy being retransmitted. There's no question we have disturbed the greenhouse effect, the blanketing effect of the Earth, water. I mean, it's really a blanket that's retaining extra heat on the Earth. We've disturbed that, we've enhanced it. So we are now retaining an extra 3 watts per square meter in the Earth's biosphere, which is causing global warming. That is less than 1% of the incident solar radiation. So we've got an imperative, an urgent imperative to rebalance that 342 watts coming in and 342 watts going out, but the task is less than 1% of that agenda. So again, all we have to do is, can we recalibrate and put 1% of extra incident solar radiation back out to space? We previously mentioned that we've got 24% of that 342 watts, 85 watts per square meter at the moment being transpired through these latent heat fluxes through transpiration. You know, the 590 calories going up with every gram of water. So hang on, there's 24% through that process. We need to increase it 1% more. So effectively a 3-4% increase in transpiration would balance that 3 watts per square meter, or to put that extra 3 watts per square meter back out to space. So when we broaden the context, when we look at this at a natural climate change on a natural context rather than our dogma about CO2 greenhouse, then the answer is very simple. Yes, we need a 1% correction. The green vegetation already does 24% of that correction. So if we bring that up a little bit through just regenerating more land surface, we can safely, naturally cool the planet. Now, this is just one of the processes. There's about 8 different stages in which hydrology governs and regulates that 342 watts going back out to space. We can go into all the details, but for us, the really powerful, empowering, wonderful, and safe option is to say, right, how do we simply understand what's going on, look at these natural processes and say, look, what have we done to disturb them, and how can we simply, naturally, safely restore them so that we can cool this planet? Again, the good news is, yes, we can. We can easily put that 3 watts per square meter back out to space, and we can do it within weeks, within months. And it seems a bit obscene, doesn't it, to say, look, here, we can do it within weeks and months, when we've been talking about 50 years of flogging ourselves, 25 COP processes, and when we come to the scientific acknowledgement that even that is just impossible because it'll take thousands of years because of the ocean lag and buffer effects. Okay, so really that's the message. yes, we can safely cool it, we can do it rapidly, but also much, much more importantly on that, and then that scale. What has happened, and this is really quite interesting sociologically, what has happened, of course, we've said we've had a global emergency. And so what's happened is to say we have to solve this at a global level. And of course, to do that, we said, look, we need to have international consensus to have a global solution. So we immediately put all our future into this oxymoron, because international consensus, by definition, is impossible, because we've got a whole lot of competitive vested interests that are deliberately, and for 50 years, deliberately been perverting any concept of international consensus, because it's not in their individual vested interest. And so we've completely disempowered ourselves for 50 years, where we're waiting for politicians to do something that they can't do. I mean, politicians are there in a democracy on a short-term, expedient, opportunistic, populist, media-driven dogma. They can't talk about 100-year strategic change in ecological factors because, hey, it's incompatible with their 3-year survival instinct. And of course, this is just one politician's. The idea that we're going to get 200 politicians all agreeing on that is, again, an oxymoron. And so we've disempowered ourselves. And so really the big message is to catalyze the changes, to cool the planet within the months that we have to and can do, and we do have to do it. Quite frankly, this is a decade. If we haven't fixed this by 2025, if we haven't changed the basis of these hydrological climate drivers by 2025, I'm afraid nature will take us out. Biosystems will collapse with more and more wildfires. Not just Australia, it's Portugal, it's Greece, it's California, Alaska, Siberia, the Amazon, everywhere. Biosystems are collapsing, extinctions are happening, and if we haven't fixed it by 2025 and reverted things back to nature and stability, we are actually making Homo hubris a very, very threatened species, right? We've got to get back to Homo sapien, conscious, sentient, intelligent, responsive to actual natural reality. But to do that, we have to empower ourselves. We have to say, look, the action, the decision point is back with us at the grassroots, at the community empowerment level. And it's really what you do at every level, locally, at a community transition level, is where the power is. Whether you have urban agriculture on your balcony, in your courtyard, on your streetscape, it's what you do rewilding those vacant areas around you. It's all those local actions, because the whole bottom line is regenerate the Earth's soil carbon sponge and enhance the longevity of green growth on this planet everywhere, because that's what's driving the hydrology of the planet. That's what's driving the cooling of the planet. And basically, with that regeneration of the Earth's soil carbon sponge, we can actually safely, naturally cool the planet, as we said, within months. So look, as way of introduction, I think that's, in a sense, where I come from, the way I see it, the opportunities I think we can bring globally, but not globally in the context we talk politically, more or less globally empowering the grassroots. And it's wonderful to have this webinar and have people from, Scandinavia and Ireland and Europe and America, everywhere coming into it. But it's how do we empower grassroots social action, regeneration, rehydration, regreening, rewilding. And of course, then we open up this wonderful plurality of different movements or different interests, whether permaculture, biodynamics, holistic management, all the different sort of areas where people have been looking at the same principles, the same regeneration, rehydration principles, but from different contexts according to what the situation is, whether it's grazing or forests or whatever. So it's really bringing this grassroots community empowerment, as Paul Hawkins says, this blessed unrest, these millions of NGOs and community groups, and bringing all that energy and all that potential around a simple message: regenerate the Earth's soil carbon sponge. Stop looking at CO2 as a pollutant. Stop looking at it as a symptom. Say, no, this is just a simple, natural, organic chemical that we can basically harvest through plants, as nature's done, to rebuild the Earth's soil carbon sponge, and through that rebuild the Earth's hydrology and safe natural cooling. Okay, so I'll stop there for the moment, but then let's start asking the questions. Now, it's fair comment to say that we can go into the technical details. We can go, all this stuff is totally documented, peer-reviewed, scientifically published. Most of it is actually published way before this current hiatus into, the CO2 greenhouse crisis problem. It's all climatology 101, but we're very happy to go through in great detail all the technical, physical processes, but perhaps not easily on this webinar. But the most important thing at the moment is really just listening to your questions, because that's really the front edge of change, and then saying, okay, how do we answer those questions? How do we empower and catalyze action for everybody in each of their situations? So over to you, Sheila and Christopher.
So Walter, thank you for that. I love your optimism, and I really appreciate that elegant simplicity when we understand how life works. And I just want to take a sentence out of your paper, Regenerate Earth, which I'm hoping that everybody on the call has read. But you've got a lovely little sentence in there which says, how the future plays out depends on us. So with that message, I want to turn the call over to the about 150 participants, Walter. And as you're talking, I'm imagining you've got 150 very curious individuals who want to take the messages from today and apply it in their own locality. So I'm going to kick off with the first question. How do you create the sponge or any carbon from any plants in the desert area that is lacking water?
Right. Well, look, this is wonderful. And it's this whole question, isn't it? Like, well, two things. I mean, like, if you wanted to go there, you wouldn't start here. So the answer is yes, you're in the desert. Sure, that's difficult. And so, yes, you've got a very difficult situation. So is it the best place to start, or do you start at the edge of the desert, right? Do you start at where it is desertifying, where there is residual green vegetation that's going backwards? And so rather than starting in a bare hard desert, can I start at that edge and actually turn that edge back towards regreening rather than desertification? The second thing is there's a beautiful old Chinese proverb, when is it the best time to plant a tree? And the answer is 20 years ago. But the second best time to plant a tree is now. And so we don't run away from it. So with the deserts, it's very, very important. And actually, we're very, very much involved with this whole area of arid zone rehydration, regeneration. Just in terms of context, there's 14 billion hectares of land on this earth. That's it. No, not making any more of it. Some of it's going underwater because of ocean sea level rise. Okay, 14 billion hectares of land. We have, in the last 8,000 years, turned 5 billion hectares of that 14 billion, about 40%, into man-made desert and wasteland, right? So these deserts are a factor of human creation, of mismanagement. The Sahara 9,000 years ago was a verdant savanna. Okay, all the fossils are still there, all the pollen analysis is still there, all the drawings on caves are still there. It basically it was vegetated and was hydrated, and it was a healthy savanna. I come from Australia. Australia is the driest inhabited continent. We've got deserts, vast areas under 100 millimeters per year of rainfall, so well and truly desert, drier than many other areas. But 95% of Australia's deserts are still vegetated. Okay, they still have vegetation. Now, we can go into a lot of details here. It's quite exquisitely sophisticated, but basically plants are harvesting water in a very, very sophisticated, efficient way. I mean, these desert plants have what, again, I'm going into the details. Some of you will get it, others perhaps not, but they have very sophisticated mycorrhizal symbionts. These are fungal networks that they have, and these fungal networks proliferate throughout the soil from the desert plant, the roots of the desert plants, and these mycorrhizal hyphae proliferate throughout the soil, and they're able to take up water from soil films at 3-4 times the water tensions that plants already have gone to wilting point in. Okay, so plants can take water from soils to a certain tension. These fungi can go much, much, much further, but they're also much more extensive in harvesting water. So in a sense, here are mechanisms through which these desert plants harvest water. Again, it's, as we talked about with climate change and CO2, it's a matter of context. Okay, we always see water as a liquid, don't we? I mean, we say, look, we need water, and so, hey, we've got to turn on the tap, or it's in a dam, or it's in rain. We always see water as liquid. But of course, desert plants don't do that. They don't just rely on liquid water. Most of you are sitting down, so that's good. So it's good to be sitting down, because what I'm going to say is a bit upstarting. Because the answer is there are rivers of water flowing across all the Earth's deserts continually through the water vapor in the air. Up to 50,000 parts per million of the weight of air is water in the form of water vapor. Now, it's not that everywhere, but up to 5% of the weight of the air is water. And that air is flowing continually across the deserts. Most of the world's deserts have got high humidities, especially in summer. In fact, we end up now with these very dangerous humid heat, conditions, but that's another thing in terms of health. But the point is, there's 5%, up to 5% of the weight of that air continually flowing across the world's deserts is made of water. And of course, if we look at desert plants, hey, thank you very much. Where do you think the cacti get their water from? They're absorbing that water vapor from the air continually every night, hygroscopically, osmotically, sucking it up in their tissues. Where do you think all the salt bushes and all the sort of cactusy type plants, the fleshy type desert plants get their water from? They're continually harvesting and sucking in that water. They can create cooler surfaces and condense dew in deserts. 1 to 2 millimeters of water per night. So that on a 200 night sort of harvesting mission, that's 8 inches, 200 millimeters of water. I mean, that's swimming pool stuff, luxury, isn't it? So the point is that, you see, we see things in such narrow ways that we humans look at water as liquid. Hey, there's no liquid water, in these deserts. Hey, we give up. And the answer is plants don't give up. 95% of Australia is vegetated, green, even where it's desert, because it's harvesting water through these very, very smart mechanisms. And all we have to do is look at nature. How do plants survive? And how do we now basically use those processes, regenerate those processes to rehydrate or to regenerate plants and deserts, and through that rehydrate and regreen those deserts. Next question, or another follow-up question, Chris, if you want.
Yeah, it creates a wonderful image, Walter, the rivers of water running around the planet. And what I hear you say is basically the water is that the water vapor is there, ready for us to utilize. And I think that links to the next question. I think it's a question from Australia. does Walter have a way to work out the brittleness index mathematically? If he has the TOC, total organic carbon, in the top 30 centimeters, the humidity, and the albedo surface temperature data? So it's a big question. So
yeah, look,
it links to what we were talking about in terms of hydration.
Yeah. Okay. So look. Okay. So this is a question that we can't really answer it on a webinar. Simply when we come to formulas and mathematical sort of equations. The point of brittleness is, yeah, obviously different environments, especially seasonally wet, dry environments, are much more brittle, or risk being much more brittle than what we previously had is green environments, which were, in a sense, relied on regular moisture input, and so they were seen to be much more resilient rather than brittle. But quite frankly, I mean, I know that concept applies, but I think what's happening now with climate change, and this is really the bigger message, the thing that's happening with climate change, we mustn't assume that the reliable rainfall that we got to give us a resilient climate or brittle climate is going to stay around. I think we're going to be in a position of dangerous hydrological climate extremes occurring right across the planet and intensifying. So we've got to really basically get back to saying, rather than, hang on, here's my metric, my score, am I brittle or not, or do I have to worry or not? The answer is, how do I actually build resilience everywhere in every situation? And that's simply a matter to ensure that every raindrop, every bit of water that you do get is actually retained, conserved, and used efficiently in that site rather than lost. Okay, so it's a question of saying, okay, have I got my sponges that are able to absorb water? Have I got my green vegetation cover that is able to stop so much evaporation and desiccation? Am I retaining whatever rain I get? And am I creating resilience in that biosystem I create, rather than going on a metric, a score to say, oh, I'm in a non-brittle environment, therefore I'm safe. Chris lives in Cumbria, in Penrith, beautiful, beautiful country. And of course, it was non-brittle because it basically assumes that it's going to get sort of mist and rain every 3-4 days, and it'll then stay verdant and green. And of course, it's been doing that for 2,000 years, since Roman times, when the Romans cleaned the forest. And it's maintained as green, verdant, beautiful lake district pastures. But you see, if now with climate change, all of a sudden the lake districts gets 4 weeks of dry, hot, windy weather, the lake district will turn brittle rapidly, dangerously. And so I think, so what I'm trying to get at, let's get back to the primary process, and that's resilience, hydration, conservation of water in the sponge, making sure every 100 raindrops we get is utilized efficiently rather than lost through runoff and evaporation. And that way we can basically ensure that we've got the best hydration, the best resilience in our landscape. Now, I can come back to the people asking this question on brittleness and indexes and stuff, but it's a little bit sort of too obtuse to sort of talk about verbally in the webinar beyond what I've said, I think. I hope that helps.
Okay, well, it is perfect, Walter. And obviously, what you're saying is that even though the ground might be brown and brittle in terms of the plant life, there's oceans and rivers of water flowing over and over.
Yeah,
so
and
we
also
get the point
it's
on
a
that
question
one.
then of making sure that we don't manage the biosystem so harshly that we don't accelerate the evaporation, desiccation of that landscape, that we keep it in a very buffered, conservative state as a shelter would that can actually retain more water.
Right. So this topic then leads us nicely into the next question. And it says, hi, Walter, what's your take on what's going on with the fires in Australia?
Right. Okay. Thank you very much. And look, I've been very, very much involved with fire for the last 50 years because it's an absolute integral part of Australia's fire ecology, in fact, all over the planet. Okay, it goes back, as I sort of said in the beginning, 420 million years ago, we had rock and ocean, no life on land, pedogenesis, fungi, lichens, created soils, created terrestrial biosystems. And so through the Carboniferous, you know, that next 100 million years, we had prolific growth of forest all over the planet and basically a massive drawdown of CO2. CO2 got down to 100 parts per million in the atmosphere at the end of the Carboniferous, right? It was all taken up by biosystems. But when we take out too much CO2, then of course, in photosynthesis, you've got this simple equation. We're drawing down CO2, but plants then release oxygen. Oxygen went up to perhaps 25% of the atmosphere. And when oxygen goes up to 25% of the atmosphere, guess what? We get close to spontaneous combustion. Okay, things just start burning. And so we had a massive, massive extinction event between the Carboniferous and the Permian. And in fact, we nearly lost life on land totally, right? Through this massive extinction. It was the most severe extinction event the Earth has ever suffered. And it was basically due to a mega wildfire because, yeah, we basically pulled down so much carbon. We had so much fuel in these forests and such a high oxygen level that was so spontaneously combustible that we had this mega fire. And obviously nature sort of in getting smart and balancing it said, look, hey, we have to sort of regulate our fuel levels. And so it's evolved a balance, as it always does, beautifully, elegantly, between fire and fungi. Because basically, if we take all this forest fuel and we, instead of burning it, if we enhance the biodegradation of that fuel by fungi to turn that fuel into stable soil carbon, into the sponge, hey presto, we end up with reduced fuel, reduced fire risk, but we also end up with a hydrated, spongy landscape that is moister and, of course, reduces fire risk even further. And so the whole fire ecology of landscapes is governed still everywhere on the planet by fire or fungi. And where we have basically fungal activities being repressed, then we build up accumulations of litter, forest fuels, and by definition, they will burn. And as they burn, they oxidize all that carbon and actually turn that landscape back towards desert. So, you know, here's the oxidation of biomass, the oxidation of that sequestered carbon through photosynthesis, turning that environment back to mineral soil, mineral detritus, desert. Conversely, where we've got good fungal activity, we're turning that fuel into organic matter, into sponge, into more water, into more productivity because there's water, nutrient cycling. We're more or less moving that system from what was initially an arid, at-risk, brittle environment into more and more mesic environment, ending up with rainforests. Okay, and so the whole thing in Australia is exquisite because we have a continuum here between arid, desert, dry, sclerophyll, hard, harshy vegetation and rainforests on the same soil, on the same climate, totally dependent on what happens to that fuel. Does it burn and reinforce aridification and more fires, or does it turn into sponge, humic, soil, moisture, and rainforests? And what's happened in Australia is actually quite significant because, again, Australia, we've only been Europeans here for 250 years, and we've had a lot of impacts, but the basic ecology is still functioning. And what we're seeing with the fires in Australia now is actually this balance between fire and fungi having been totally perverted, okay? Because we've, in a sense, done so much disturbance, we've destroyed so much of that bioconversion capacity that we're accumulating very, very dangerous fuel levels, particularly from our eucalypts, which are just fire weeds, producing prodigious amounts of fuel, but without that fungal breakdown process dictating we're getting more and more severe wildfires. You superimpose on that climate change and increased heat and extremes, and we inevitably end up with wildfires, as nature did after the Carboniferous. And so the only solution we've got, and what this crisis in Australia is telling us, we have to reduce these fuel loads. We can't do that by controlled burning. It's too dangerous. Also, it's counterproductive because, as we said, burning just accelerates more burning. But we've got to do that through enhancing the biodegradation of this litter. And again, nature developed exquisitely efficient processes. The breakdown of that litter is dependent on a whole lot of factors, including the carbon-nitrogen ratio, so how much nitrogen is in that litter, because that helps break down that litter, and therefore how many insects and animals are defecating in that forest to add that nitrogen, to drive that cycle, how many scratchivores, birds and little animals are turning that litter around, digging for truffles and what have you, and disturbing and actually composting that litter in situ. And that was what was happening naturally, and that was actually what was driving then the balance, but also moving vegetation towards rainforest in Australia. And we've actually destroyed a lot of that, turned it in a lot drier, and now we humans are on the barbecue because we are basically now facing this higher fire danger, more pyric environment that we have created. And it's a wake-up call, it's a tipping point. If we don't change this rapidly and build this ecology back into the system, most of Australia's biosystems will burn and aridify continually, move rapidly back to desert, have massive extinction impacts, and of course completely destroy social economic potentials, right? Because just in our society, like where I am now, southern New South Wales, we've had 6 million hectares of forest burn, but with that basically has made it impossible to actually even to build a house anywhere near a forested area, because to insure a house now, and if it's going to burn or risk burning every 3 or 4 years, the insurance premium have to be 40% of replacement cost every year, which is impossible. So the whole economic viability of communities and economies crashes, because if you haven't got insurance, you haven't got finance. If you haven't got finance, you haven't got economic activity, and the whole socio-political thing goes meltdown, collapse. Okay, and therefore to avoid that, we've got to get back to say, look, rebuild the balance, fire versus fungi. So long answer to the question, very important question though. Australia is in a sense, the weather vane. These wildfires aren't unique to Australia. They're happening everywhere, but it's all around that simple natural ecology, fire versus fungi. And we're really at that razor edge of, will we learn? Will we wake up? We can do this so easily. We can so easily increase that fungal breakdown of litter. We can treat 1% of the forest area in a strategic way to create the fire control over that whole 100% of that forest area through the strategic enhancing of these biological fire breaks and biological fuel reduction strategies. But we've got to change our mindset. We've got to respect nature, get our boot off her throat, let her breathe, and really say, look, how did nature solve this? What do we have to do that as well?
So Walter, I love that question you come up with the end, that what do we need to do? And I want to shift from that beautiful picture you just created of those multiple habitats in Australia to India, which I know you just returned from.
Yeah.
Because we have someone who's posed a question and they've been observing, and it's the observations of the change with the land that's leading to this question. And it says, can you explain in some detail why increasing green cover causes more rain to fall on the farm, as I have seen on my own farm in India? My soil carbon has gone up in the last 8 years with super high density grazing, and I get more rain now with isolated showers, sometimes raining on my farm and around alone. I have seen it enough times to know I'm not imagining it. Thanks.
Right. Okay. Now, look, and thank you very much for the question. And again, this is wonderful question, but very profound, very deep. We could talk for hours about the intricacies, but let's get to the core things about it. But then, yes, there's more and more to explore, right? What the question is really saying is that, again, we just got to change our minds. We've got to open our minds, because we've assumed that the weather, rainfall, is a physical phenomena on the planet. And we sort of look at different regions of the earth and say, well, this is a wet region, this is a dry region. You know, Christopher lives in the Lake District. It's a continually moist, resilient region. And you can book, you can, you know, you can bank on that weather. And it's nothing of the sort. Rainfall is a biologically driven process, and it's enhanced or degraded depending on how we manage the landscape. We talked earlier about there was the Sahara Desert 8,000 years ago as a verdant green savanna. If you look there now in the weather of the Sahara now, you say, no way, you know, it hasn't rained for 4 years, and it's losing 3,000 millimeters of rain a year, I mean water potential a year, through evaporation if the water was there. So how can this have been a vegetated area? Why? Because that weather, the climate has changed with the vegetation. So it's not just that vegetation needs rain, rain needs vegetation. And that's everywhere, whether it's in the Amazon and the Sahara, but also in India. Okay, and I was in Andhra Pradesh in India by invitation, and very, very grateful, and was very interesting. But again, India represents one of these societies and these dry, seasonally arid sort of tropical areas where it's, again, on that cusp of, is it going towards desertification, or are we going back into regeneration? And so the secret question is, can we put green plants into that vegetation in the better seasons that have the resilience and the longevity of green, right? Can they extend the longevity of green? So the target for Vijay, my good friend in India, is 365 days green, right? So can I have agro ecosystems where I can not just have crops, but then I have 365-day green vegetation cover? Sure, it's tough, it's xeomorphic, it's struggling, but it's maintaining protective green plant cover as long as possible. And it can do that if it has deep roots, mycorrhizal symbioses, and appropriate management, right? But then when we have 365-day green, then something phenomenal happens, really phenomenal happens, right? Okay, if we have, and I'll just go through this scenario, it'll take a minute or two. If we have covered, protected land surfaces with vegetation on it, then basically that protects that soil from incident solar radiation, the 342 watts coming in. If some of that vegetation remains green and continues transpiring for as long as possible, that's taking 590 calories of heat energy from that soil surface back up into space, thereby cooling that surface. The protected plant covers also reflects albedo effect, reflects quite a lot of that incident solar radiation back up into the air. And so the heat incidence on a protected, vegetated, green surface is enormously powerful in reducing how much heat is actually going into the soil. Even in tropical areas, those soils mostly don't get much above 20 degrees centigrade in temperature. Okay? So basically we've got 342 watts coming in, but because we've got this protective insulating blanket, we've got this transpiration, we've got this albedo effect, the amount of heat getting into the soil is contained or restricted. Temperatures mostly don't go up above 20 degrees centigrade. Let's take the contrast. Where we have got a bare exposed surface next door, same soil, same environment, but we've now got a bare exposed surface, all that 342 watts per square meter of incident solar radiation is, is being absorbed by that soil, right? And those soils, and we've got soil thermometers and things, they'll go up to 70 degrees centigrade. That soil on the surface will go up to 70 degrees centigrade. Profound difference in surface temperatures. That 70 degrees temperature, of course, totally cooks the soil, kills all the microbial life, turns it effectively into a desert. The Sahara, we've got 80 degrees centigrade soils, right? So it really cooks, bakes, and desertifies. But now something much, much more profound and absolute happens, which is scary. There's a simple law of physics, right? It's basically the Stefan-Boltzmann law of black body radiators. And it sort of says basically that the amount of heat a body will re-radiate back up into the atmosphere is dependent on the temperature of that body. Okay, so the amount of re-radiation coming from a body, think of it as a stove, the amount of heat being re-radiated by a stove is dependent on the temperature. But not just the temperature, it's dependent on the fourth power of the temperature in degrees Kelvin. That's technical. But the point is it's a fourth power, temperature times temperature times temperature times temperature. So basically, it's an exponentially massive, greater amount of heat that's being re-radiated from that bare, dry soil compared to that protected soil 5 meters adjacent to it, right? Because that re-radiation, Stefan-Boltzmann equation, you can't escape it. It's like E equals mc squared. It's physics, right? It's the universe is governed by it. Okay? And so that amount of re-radiation is massively, massively higher. Now, here's two critical points that are very, very important. What is the thing that drives the greenhouse effect? And everybody will put up their hand, oh, the amount of CO2 gas molecules in the atmosphere. And of course, they're right to the extent of that governs 11% of the gas effect. Water vapor governs 80% of the gas effect. Methane and other things govern 9% of the gas effect. But by far the biggest determinant of the greenhouse effect is the amount of re-radiation from the Earth. It's how much of this re-radiated infrared energy is going up, whether the stove is on an ultra high or simmer. Okay? And we control whether that stove is on ultra high or simmer by our management of its land surface, whether it's 20 degrees centigrade or 70 degrees centigrade. So effectively, we can turn down the greenhouse effect within days by simply covering and protecting and keeping that soil at 20 degrees rather than 70 degrees. We can do that irrespective of how much CO2 is in the air, because that's only 11% of the CO2 gas absorption. But I mean, the greenhouse effect is simply how much of the re-radiated energy is absorbed by these gases. If there's very, very much less energy being re-radiated, it doesn't matter how much CO2 you've got up there, right? Because the heat retention total is actually massively reduced. Okay, so here we are. You have the lever, you have the control on the intensity of the greenhouse effect in your region simply by how you manage your lawn or your land surface. Have you got asphalt, concrete, bare soils heating up to 70 degrees, 60 degrees centigrade, or have you got green grass with tree cover where it rarely gets above 20 degrees? So you govern the actual heating of this planet on every square meter of exposed surface and the temperature that that surface is. It's got nothing to do with the IPCC. It's got nothing to do with international politics. It's got nothing to do with oxymorons. You are empowered, but being empowered, you are also responsible. Every person, every square meter on this planet. We are empowered. We are able. We are response-able, not just responsible. We are response-able. Okay, so that's the first part. The second part is even more profound. When a hot area like this re-radiates energy back up into space, obviously massive amounts of heat are going up into the air above that region. And that creates a high pressure heat dome over that region, right? Clearly, hot, hot, hot air being re-radiated, high pressure, because pressure is a matter of temperature, so it's a high pressure heat dome over the region. So we have high pressure heat dome or high pressure zones, zones over that region. Now, it's a simple physical reality that low pressure air, low, moist, cooler, low pressure air can't replace or dispel high pressure zones, right? It goes the other way. High pressure flows to low pressure. Low pressure doesn't flow into high pressure, just physics. And so basically these high pressure heat domes over these bare exposed areas will flow out and actually block any inflow of cool, moist air from maritime or other sources, right? So deserts create deserts. Deserts reinforce deserts because by heating up, by re-radiating, by creating these high pressure heat domes, they actually block inflow of cool, moist air. Therefore, by definition, they aridify. So desert desertifies, right? And obviously, the converse also happens. If we can create green, moist vegetation, right, and especially if we can harvest some of that moisture that goes up in the air, then we're creating lower pressure because we're taking that moisture out of the air. We haven't put so much in, but we're also taking moisture out. And so we're creating these low pressure zones, corridors, where more moist, cool air can flow in. And so we're creating actually this dynamic whereby, green begets green. Green valleys will encourage more green or moisture inflow and more green valleys. Conversely, dry, hot deserts will actually block inflows. So these are the biotic pump effects. And the Amazon, for example, is a rainforest right across America, South America, that gets basically so much water coming in from the Atlantic, but because it's raining and green and all the time, it's cycling water continually through that forest, and it's just drawing in more and more water from the Atlantic Ocean into the Amazon continually through these biotic pump effects. Up to the last couple of years, we've never had hurricanes in the South Atlantic because all that moist air that could generate a hurricane was always drawn into the Amazon basin to hydrate the Amazon. And so there was never enough moisture building up on the South Atlantic to ever generate a hurricane because the forest was stealing it all through these biotic pump suction effects. Okay, so the story is very simply that basically if we want to rehydrate arid areas, we've got to increase the longevity of green, the 365 days green. We've got to keep that soil cool, and therefore we've got to enhance and encourage these cool, moist air flows, and we talked about them, the 5% of moisture that's flowing across the air continually, 5% of moisture that's coming through in our rivers in the air. And we've got to encourage these rivers coming into these areas by keeping cool, verdant, green habitats rather than the hot, dry, high-pressure heat dome. This process that we've just talked about of, like heat dynamics is in a sense what monsoons are, right? The monsoons that we talk about, again, as physical phenomena, they're real, they're absolutely powerful, but they are just the consequences of these heating, cooling dynamics on the planet. And so through our land management, we significantly influence our monsoons. We used to have a Sahara monsoon, or a monsoon in northeast Africa. We used to have the intertropical conversions coming up higher, but we killed that because we basically bared the landscape. India still has a monsoon because, again, the Himalayas is an orographic effect, but also because of its cool, verdant thing, sucking air in every summer in the Indian monsoon. But we risk now changing these monsoons through our impact on land management. It's very, very serious. Basically, there'll be 4 billion people on the planet whose existence depends on the reliability and the degree to which that Indian monsoon operates every year. So 4 billion people at risk if that monsoon goes. And of course, we are, in a sense, a direct agent in that monsoonal cloud rainfall dynamics. So coming back to the question, yes, how do we revegetate arid areas? The answer is yes, we've got to encourage green. We've got to go to the edges of them where basically this brittle, as we talked about with the fire effect is happening, with brittle aridification or mesic effect is happening. We've got to tip it more towards more green, and that green will encourage more rain, and at a larger scale, it actually governs monsoons. So hopefully that's not too long, but it's very, very profound.
Again, certain hope in an uncertain world, as our friend in India realizes he can call in the rain, Walter.
Yeah, well, I mean, that gets a bit freaky, doesn't it? I mean, like, okay, this is Homo hubris again. Not that he is, but we've got to be very, very careful. Look, we've got to understand this is how nature operates. Look, nature just started off with a rock, CO2, water, sunshine, minerals, stardust. Here's a rock, and basically has created all these hydrological and bioprocesses through very, very simple combinations of physical factors, right? So when you get to the essence, it's that simple, but then it comes so profound as your question, are we actually calling in the rain? And the answer is yes, we do. And of course, that's what First Nations mythology, First Nations knowledge has all been about for thousands of years, right? How do we, in our caring for country, govern and regulate and influence these bigger planetary systems?
So questions about carbon. There's a whole cluster of questions which one specifically asks about, is there a fixed amount of carbon on the planet? But then other questions cover, if you look at soil, trees, grass, which is the more effective storage and processing of carbon?
Right. Okay. Look, thank you again. Very important. And let's get to this quickly. Yes, there's a fixed amount of carbon on this planet. Okay. Basically 4.6 billion years ago, big supernova, big explosion, created a cloud of hydrogen gas, which formed our current sun, and a whole lot of stardust. That stardust is basically made up of, the elements in the periodic table, including carbon, of course. So there's a fixed amount of carbon. Most of that carbon was in the atmosphere as CO2 and methane originally. But progressively, of course, what's happened is nature, biology, has actually then drawn it down. Okay, 3.5 billion years ago, photosynthesis. And here's a process now whereby we can take carbon from the air and make carbohydrates, make sugars, and of course carbohydrates, and start sort of basically fixing that carbon. As we said, 420 million years ago, we had the colonization of the rock, the land and forests, and that was then a profound effect, because then we had forests, but also we had these fungi that were able to then biosequester carbon from sugar, cellulose, lignin, and make coal and fossil fuels. And so now we've stored about 15,000 billion tons of carbon as fossil fuels, and well, sorry, no, about 5,000, oh, okay, break it out. About 15,000 coal and oil, plus another 15,000 billion tons as methane hydrates on the continental shelf. So no prodigious amounts stored as biological carbon, right? We've now got basically 700, okay, just in quantity, 750 billion tons of carbon in the atmosphere, about the same roughly in our living forest green vegetation. As I said, we've got these fossil fuel carbon sinks, you know, about 30 billion tons altogether. We've got 38,000 billion tons locked up in the, or not, dissolved in the Earth's oceans. And then, of course, again, I forgot to mention this, we've actually taken millions of billions of tons of carbon out of the air and fixed that minerally and minerals, again, biologically, in chalk, limestone, corals. And again, over the last, you know, billions of years, it's these ocean carbon sequestration processes making limestone and coral that is actually the biggest sink of carbon on this planet. But all that sort of said, so this is in a sense the pools of carbon that we've got. But we're not going to change that. Well, I mean, we are changing it, especially if the methane hydrates sort of come up and cook us all. But the point is, the point of agency that we have got is actually vegetation and CO2 in the air, and how much of that can we draw down? And again, it's, as in nature, very, very simple. Basically, it's photosynthesis. Okay, it's how much carbon or how much photosynthesis is occurring on the planet. And we've been talking about that as the longevity of green, you know, how much area, longevity and efficiency of photosynthesis that we've got on the planet. And that's in a sense drawing carbon from the air down into sugars, cellulose, lignin. But that's only part of the equation, right? That's only the starting point. That's the fixation of carbon. What's more profound is what we already talked about, is what happens to every molecule, every gram of carbon that photosynthesis fixes on this planet. And that's really the cardinal issue. Does it burn, or does it biosequester into stable soil carbon through fungi? See, that was the fire story we talked about earlier. Burn, you know, fire or fungi, burn or biodecompose. So it's what happens to that gram, each gram of carbon. Does it either burn, oxidize, or does it go into soil carbon? The way we run our agriculture and land management at the moment, for the last 200 years on this planet, we have been oxidizing most of the carbon that the land produces, and also lots of our heritage legacy carbon and lots of our carbon in fossil fuel stores, right? So the fact that CO2 has gone up is because we are oxidizing carbon at a much, much higher rate than nature is actually drawing it down. Therefore, CO2 has gone up to 415 parts per million rather than 300 parts per million 100 years ago. Okay, and so we are actually in a farming situation, because of our oxidative land management practices, probably putting 150% of the photosynthetic yield of that land back up into the air as CO2. And we do that, you know, when we cultivate, when we over-fertilize, when we add biocides, when we bear fallow, you know, we're basically putting carbon from that soil back into the air, increasing that. And all those activities, of course, need fossil fuels. We're still using 10 units of fossil fuel energy to grow 1 unit of food energy. So it's a massively subsidized, ridiculous, unsustainable industrial agriculture that we're running. Conversely, though, we can, in a sense, say, look, for every gram of carbon photosynthesis fixes, we can say, yeah, look, we can put 50, 60, 70% of that underground into the soil carbon sponge, and that rebuilds soil capital, that rebuilds hydrology, that rebuilds productivity, that rebuilds resilience. And in a sense, we move that biosystem, as we talked in the last question, from desert to vegetation, we move that system more and more to greener, more mesic, rainforest type, climax communities. So it's that simple fire versus fungi again. Do we burn or do we biodegrade? And if we put more focus on biodegrading, then we can turn that whole balance around. The biodegrading is done basically by fungi. That's why fire and fungi are the key issue. And there's two key groups of fungi. There's the humus-forming fungi, the higher basidiomycetes, that are turning cellulose lignin into humates. And they're going to be stable in soil for 100 to 1,000 years. And there's another group of fungi, the mycorrhizal, vesicular buscular mycorrhizae, that basically use about 40% of the photosynthate from plants that leaks out as exudates from the roots. It commandeers most of this and basically produces its own networks of fungal hyphae throughout the soil. And when they break down, they produce another stable carbon called glomalin. It's a polypeptide. And basically that glomalin, again, is a key, up to 60% of that stable soil carbon pool. So basically, how do we grow soil carbon? How do we build sponges? It's maximizing photosynthesis, but it's then managing landscapes so we do less oxidation, we do less burning, and more fungal biodegradation to build these humus and glomalin stable soil carbon sinks. So it's that simple, right? It's a simple matter of, maximize green and then stop doing stupid things that excessively oxidize. There's no harm in having, well, it's essential that we need some oxidation because otherwise we would run out of CO2 in the air to photosynthesize. And of course, every time we breathe out, we are actually breathing out 1,000 parts per million CO2 because we've used those sugars as our energy food. So respiration is a major input into that CO2 back into the air. But of course, we need that. That's life. If we go back to Charles Keeling, basically 50 years ago, he showed it all so elegantly. He had a beautiful diagram. CO2 was going up, but he had obviously every year, you will remember seeing those annual peaks, right? And those annual peaks were showing how basically, particularly in the Northern Hemisphere, every winter we had a net emissions of CO2. So every year we were emitting about 130 billion tons of CO2 going into the air. And every year the residual biosystems on this planet were drawing down about 120 billion tons of carbon a year globally. And that was, in a sense, resulting in about a 10 billion ton deficit between our emissions were higher than the drawdown. Okay, and it's that 10 billion tons accumulating year after year, which has, of course, increased the CO2 in the atmosphere. And also, of course, a lot of it's gone into the oceans, absorbed into the oceans. But in a sense, that rise in CO2 has been driven, as Charles Keeling showed us, by the imbalance between our emissions and our residual drawdown. There's 130 going out, 120 coming back in, 10 residual. But basically, we can change that really easily, and that's what the Regenerate Earth paper is all about. Because here's 150 or 250 billion ton flux out and in, and we govern each of those processes by simply stopping, for example, burning of forests. Every year 350 billion hectares of forest burn and probably emit 50 to 200 tons of carbon per hectare. So there's more CO2 going into the atmosphere from forest burning in bad seasons than there is from our fossil fuel use. But we know we can stop that forest, not stop totally, but we can vastly reduce that forest burning. Holistic management comes into this. Alan Savory sort of makes, I mean, we know for a long time, but Alan reinforces the point, up to 2 billion hectares of grasslands burns every year, grasslands and crop stubbles. Africa burns over 1 billion hectares. Okay, and basically when those grasslands burn, 5 to 10 tons of carbon per hectare are emitted back into the atmosphere through that burning per hectare. So again, there's more CO2 going up from grassland burning globally and stubble burning than there is from fossil fuels. Okay, 2 billion hectares times 5, that's 10 billion tons of carbon, equivalent to the fossil fuels. And we can stop all that easily. Why? How? As nature did, because nature evolved these mobile compost heaps, these mobile bioreactors. And we've got these beautiful mobile all over the planet, and they, of course, eat this grass, ferment it in their rumens, and then excrete it as biofertilizer, and in the same point produce protein. They don't have wheels, they've got legs, and they're called herbivores. They're called cattle, wildebeest, zebra, gazelles, herbivores, insects. So the whole point is that it's burn or biodegrade, but these herbivores, this ecological grazing management, we've got about 5 billion hectares of grassland, residual grassland, rangeland on this planet. All of that is dependent on its herbivores and on these ecological holistic management practices to optimally bioconvert that grassland through animals, through these mobile biodigesters, rather than let it burn. And in the process, we're getting biofertilizers and we're getting high quality protein. Every one of us needs 150 grams of high quality protein every day. Okay, and so nature is exquisite. Here's a solution: ecological grazing, and we can save as many fossil fuel emissions or many CO2 emissions as stopping fossil fuel use without crashing social stability from pulling the rug of fossil fuels from under our 7.5 billion people. So look, that's a journey through some of that carbon dynamics, in a sense, what happened in nature, but really that critical process of maximizing photosynthesis, minimizing oxidation, maximizing fungal breakdown. And again, we can do that every square meter, every place where we are. Instead of burning autumn leaves, we mulch them. Instead of, putting our organic waste into landfill, we put it through vermiculture, compost it. Instead of burning grasslands, we've got herbivores. So we are in control. Nature's given these exquisite, efficient tools to turn all of this into stable soil carbon, rehydrate the planet, cool the planet, secure a future for the 10 billion people by 2050. The only thing we haven't got is time. And the question, and this is for you, Christopher, the question, will humanity wake up in time?
Right. Well, one of the ways in which our leaders in Davos are suggesting is it'll be through taxation they wake us up. We've got big conversations about carbon tax. We've even got conversations about meat tax. So just take that question then in terms of how to stimulate a response at grassroots level or at a multinational level. What's your views on carbon tax and meat tax?
Right. Look, yeah, it's again a very, very big quagmire, quicksand swamp you want me to swim across, right?
Yes.
But look, let's go there. Yeah, look, we've been here now. It's tragic. No, we've been here for 30 years, right? James Hansen, 1988, went to the US government and laid it all out. Here's climate change, etc., etc. We then agreed at Rio 1992 that yes, we need to do something about it. We need to put price signals and incentives to actually draw down this carbon, right? To rebuild this balance, to draw down carbon. All this Charles Keeling stuff, everyone understands it, right? I mean, not now. I mean, it was there as climatology 101. We're now so fixated we've lost sight of it. But the point is, Rio did that, and of course then we had the Kyoto Accord, and of course we said, yep, okay, all the nations will do this. But what we've learned over the last 30 years post-Rio is that, yes, this, politics, this oxymoron of international consensus. So they talk, they kick the can down the road, they talk more, they run another. You're going to have COP26 in England this year, right? COP26.
Yes.
My goodness, they're running out of 5-star resorts to hold them in, right? Where next? You'll be back to Paris, you see. But Paris, again, we had a promise of zero net carbon emission accounting, right? And again, we completely corrupted that over the last 4 COP meetings, because all they could come down to is that, yeah, we've got an aspirational target, emission reduction target, but we're not going to have any rigorous accountable mechanism. We'll leave it up to every nation to fudge their own figures, to put in their own standards, to make their own assumptions and claim about what they're achieving, which is completely pointless, useless. So after 30 years, we've got nowhere. And sure, Davos talks more taxes, etc., etc. But whether it'll happen, it's beyond the issue now, because the issue now is we have a decade, 2020 to 2030. If we haven't actually restored the thing physically on the ground, if we haven't rebuilt the sponge, the hydrology, the cooling, the buffering, the resilience in biosystems on the ground at that grassroots level in the next 5 years, so we can start getting the dividends by 2030, the real risk is these dangerous hydrological climate extremes will crunch us all, will either flood us, drown us, or burn us, right? Aridify or burn us. And so the answer is no, I don't have much faith in taxes. I was very much involved 15 years ago when our Prime Minister, Julia Gillard, put in a carbon tax. It had massive flaws in it. It wasn't the smartest thing. But the point is that it was an attempt to do the right thing. So I don't think that's going to work. We've had farmers for, again, 15, 20 years looking at, I can grow carbon. Have I got a market to do accounting and trading of that carbon? And again, it's got no further. 20 years ago, we were talking about carbon, commercial carbon trading systems. We're still talking now. What's behind it all, Christopher, is actually something more serious. It's actually that whole perversion of our accounting, because what's needed is to rebuild natural capital. Now, what we've been talking about is rebuilding the sponge, the hydrology, the resilience on every square meter, every courtyard, every backyard, every farm, every village, every region, right? It's rebuilding natural capital as nature demonstrates and has given us the tools to do. But that's what we've got to do rather than carbon taxes, because what's happening with the carbon taxes, they're basically just another financial mechanism for, I suppose, externalizing the responsibility, right? That is us just saying, right, okay, okay, I mean, well, what we've done for the last 200 years, if we get back to the basics of it, is that we've said, look, we have got these fantastic growth prospects, but all the liabilities and the consequences from them, we will simply externalize to the future, to the environment, to our children, right? All the costs and liabilities are really put off the balance sheet, and all we look at is the profit. So the whole basis of capitalism, tragically, it hasn't been what Adam Smith wrote. It's all been about how do we actually corporatize the profits and socialize the liabilities and losses, right? And that's really what's been going on. And the whole carbon tax and stuff is still just that same discussion. How do we actually, fudge around with the financial messages to try and keep the protected, subsidized status quo going, when, as we said, industrial agriculture, it's still a 10-to-1 fossil fuel subsidization of the food energy we're producing, totally unsustainable. You see, and so it's really trying to perpetuate those externalized liabilities. At the end of the day, it would be wonderful to have the incentive of a valid carbon price in the marketplace. If we had a commercial carbon trading system where a farmer could say, look, I've verified I've produced so many tons of carbon offsets, you give me money for that because that helps me do more of the good stuff, that would be wonderful. But the question is, when and will ever politics get to that point? It's questionable, but also now, in a sense, it's too late, because we've got 10 years just to get action on the ground at that grassroots level, building the sponge, building resilience, building hydrology, building cooling. Okay, so it's a diversion, because we're sort of saying, oh, as the last 30 years since Rio, you know, we're waiting, we're hoping, we're looking, but at the same time we're not doing. And I think it's really now grassroots empowerment doing that is a critical thing.
Yeah, and Walter, I mean, if we just say that what you just really said is that the carbon tax is really externalizing responsibility and the costs. The meat tax seems to be different, because that seems to take us more into a conversation about the ability of science to provide us with the approaches we need that regenerate Earth.
Yeah, look, yeah, the meat tax is a little bit different. I think again there it's a matter of reframing the debate back into nature rather than this very misleading context we've had. Look, we all need protein. We all need 150 grams of high quality protein. There's some amino acids we can only get from, you know, this high quality animal protein or microbial protein. We're not going to get it from beans, right? And so that's the simple reality, that we're an omnivore and this is our requirement. So not that we have to live off steaks all the time, but yes, certainly herbivores are important as a food source. Secondly, basically, as I said, we've got about 5 billion hectares of grasslands on this planet. Those grasslands are in absolute symbiotic interdependence with their herbivores. If we don't have herbivores on those grasslands, they burn and go to desert. We lose them, we go to desert. Okay, so we need those herbivores. Now, if we're going to have herbivores, we're going to need carnivores, because there's no way you can manage herbivores unless somebody is eating all this protein produced by these biodigesters, right? Okay, and so whether it's insects or whether it's worms or whether it's cattle is not the point. The point is that we need these herbivores to maintain that ecosystem, and we need carnivores to eat to keep that healthy herbivore population. So if we look at meat eating in that context, our nutritional requirements and our ecological requirements, then we have to sort of say, well, look, what's the negative about it? And then people say, oh, yeah, these things emit methane. And of course they do. We emit methane, you know, when we have digestion of carbohydrates, right? But the point is that the amount of methane they emit is 1/100th of the methane photooxidation activity they generate. So their net methane effect is -99 equivalent, right? Methane all through the last millions of years was 700 parts per billion. We could hardly measure it in the air. Certainly it's gone up a little bit, but that's because of fugitive fracking and gas emissions, not because of herbivores. There's less herbivores on the planet now than there were 200 years ago, right? So it's not that herbivores have gone up creating more methane. Basically, it's our management of our gas industry that's caused methane to go up. So methane is a total furphy. It's actually being pushed by exactly that gas industry to basically say, look, all the fugitive emissions from our gas leaks, let's blame the cattle because that sort of basically diverts social, reaction onto grazing rather than on this gas industry. But that's politics. The point is that if we look at cattle, what's wrong, or herbivores, what's wrong with them, the answer is nothing, right? And so that's the critical message. If we look at that methane problem in reality, graziers should be sending invoices into governments for the methane photooxidation services generated by their herbivores. Because obviously it's the cattle that maintain green pastures, it's the pastures that are transpiring water, it's the water interacting with the solar energy in the atmosphere that is creating the hydroxyl ions that eat up all the world's methane, which keep methane at very, very low parts per billion levels. So it's actually the cattle that are generating that methane cleanup mechanism, not just methane, but these hydroxyl ions in the air clean up all the atmospheric pollutants. So they're acting as the atmospheric laundry, the atmospheric cleanup service. So I'm waiting for all the farmers to put in invoices to governments instead of a meat tax or methane tax. Here is our methane cleanup invoice. And basically, yeah, if you want an incentive, that's where it's at. Now, we'll win this in any court case on the hard physics, the hard science, but of course, the politics are just trying to pervert the whole thing by hammering then this herbivore sector, in a sense, as a subsidy and a protection for the gas industry, right? So again,
Walter,
it's one of these, we're getting played in political perversions rather than the simple natural reality of the situation. But we need herbivores, we need protein. Without that protein, we're going to go very, very sick, and we're not going to sort of basically be able to sustain ourselves.
Yeah. So many of the questions, and we're not going to get through all the questions this evening. So for those who are on the call, we will keep the questions, and we'll make sure that there's a way of providing insight on these questions. I'll leave that to Sheila to work that one out. But Walter, the key question, that the observation is, your message is so common sense. It's so pragmatic. There isn't a place you can't go on the planet where it doesn't provide meaningful solutions. Why is it so difficult for the message to get through is one question. Secondly, who are the most antagonistic? And thirdly, on the subject of messaging, if you were to offer a message to Greta Thunberg, what would it be?
Well, okay, I've just shifted because I'm running low on battery, so I've just put it back on the charger, right? So you've just seen a different part of, hang on, I'll put this light on and it might be better. But yeah, well, what is the message to, in a sense, what is the message to the youth of the planet? And the answer is, yes, we can, right? I mean, this is a whole powerful point. We can actually do it, but we have to empower ourselves. We have to realize that, no, the solution is in our own hands. We are, in a sense, in charge. We are responsible, but we are also response-able. And not just words, but to say, look, here are the tools, the mechanisms, and we've talked about those, rebuilding the Earth's soil carbon sponge. Everybody can do that everywhere. Urban agriculture, vermiculture, like here's my compost heap, here's my worm farm, here's my veggie garden, here's my nature strip, here's my rewilding everywhere, right? So we've got that empowerment capacity through regenerative agriculture, through all these different vehicles. So wherever you are, yeah, that's all feasible, that's all potential. And really it's a matter to say, yes, you as an isolated individual, there's limits, but then collectively in a community, we have enormous leverage and influence, and we can do things at scale. And so this is where, in a sense, this grassroots community transition message is so important. And in a sense, it's already happening. And in a sense, Greta is already talking about that, and it's excellent. Keep on going. And of course, she's getting a lot of flack because, yes, it's hurting. I think the status quo, business as usual, they know it's unsustainable. But the point is, at the moment, the protection and the subsidies and the externalization of liability and costs make it very, very seductive to stay where they are. If they had to pay their real costs, they'd be out of that game in no time flat. And of course, that's in a sense the point, that they don't want to move from the status quo because it's too comfortable. But on the other hand, they know that the status quo is unsustainable. So I think it's like any innovation sequence. You got to understand that, yeah, you're a minority. There's lots of powerful vested interest. Of course, they're going to rubbish you. Of course, they're going to reject you. But in a sense, take it as a acclamation, in the sense their reaction is because what you're saying is valid, is right. Just keep on doing the thing, because as long as you keep on building and building and progressing, invariably through the back door, they're going to come and say, look, I want to have part of that action. I want to buy into this action. I want to buy into this innovation, because they know there's no other solution. Okay? And we're seeing that now. Like, I mean, we're seeing regenerative agriculture as a brand, as a word, being very, very quickly accepted. Everyone's talking about it. But the point is, the danger then comes, okay, it's got to be more than a word, more than a fig leaf. It's got to be actual practical action on the ground. And that's what we're, in a sense, really focusing on. No, it's about regenerating the Earth's soil carbon sponge, hydrology, cooling. It's actually doing it rather than just talking about it. But of course, when the more innovative from the status quo do want to come across, welcome them, because they've got the scale, the critical mass to actually then drive the tipping point for the change. So, I mean, they're all humans, and the answer is they've just been playing in a system which has been perverted, loaded, biased, subsidized, but they're realizing that at the end of the day, it's natural capital, it's resilience, it's health, it's these natural processes that are the only thing that are going to get us to a future.
Okay, well, we're in the last 15 minutes, and we want to leave the last 5 minutes for Sheila just to provide a summary of what we're doing next. So we've got 10 minutes, and there's an area that's come up in the questions a couple of times around the oceans. And the question is along the lines of, how do we basically regenerate our oceans? And specifically, the mention in the question is around the toxic ocean floors. And there's another question here that looks at, exploring your views of the merits of desalination. And obviously, ocean health and desalination go hand in hand together. The desalination question was linking to using the desalinated water to reboot biological processes in arid areas.
Okay. Well, look, they come together and very important. Okay, the oceans, of course, are critically important, as we say. 95% of the heat dynamics of the blue planet is driven by water. 71% of the Earth's surface is covered by these oceans to a depth of 4,000 meters on average. 3% of the land is covered with lakes and rivers, etc. So, yeah, that ocean water and that whole total global hydrological cycle from the oceans is critical, okay, because that drives the whole, heat dynamics of the planet. There's a really scary and way out of my league, scary reality though, but the oceans at the moment absorbing 93% of the extra heat that we are putting into this planet, right? So we have seen nothing yet as far as the climate and dangerous hydrological extreme impacts. Think of it, 93% of that extra heat is being heated up or retained in the oceans, and when it starts boiling or when it starts, expressing itself, it's going to be amazing and dangerous, right? So hurricanes, cyclones, everything, we just don't know what's going to happen. The big danger is if it heats up that much that these methane hydrates, the 15,000 billion tons of methane hydrates in the ocean shells, if they sort of release, and they are already going up in the Arctic, then it could be amazingly dangerous, where methane does spike, and then we'll be looking at our cows, our herbivores, and their photo oxidation potential for methane, to be the only thing that could save this planet, right? Bit of a paradox. But okay, let's get back to oceans. So yeah, oceans are critically important. What's happened is through the 19th century, we effectively sterilized the oceans, and we're realizing that now, obviously overfishing. But what we really did is we killed it with whaling, right? Because the studies are now quite wonderfully illustrative that in fact it was the excreta from whales, okay, the actual excreta from the whales basically that drive the whole global ocean phytoplankton bloom ecology, right? So it's the nutrients from whale excreta that allows the phytoplankton blooms to establish, and of course these phytoplankton blooms are the basic food chain for all life on the oceans. And we basically decimated 95% plus of the Earth's whales. And so when you think of what we did to changing that whole nutrient input and therefore the whole phytoplankton feed chain of the oceans, we're now, or for the last 100 years, we've been really seeing the crash of fish populations, you know, right across the planet, and the loss of ocean life right across the planet because of that decimation of whales. Thank goodness, unfortunately, it's now slowly recovering, and basically it's so significant because here's now a keystone species, and we can see through its effects, it can have profound effects. So on the one hand, we've got warming, which is creating a lot of problems, but on the other hand, can we actually slowly go back to actually raising the productivity of the oceans again because of these natural, you know, nutrient fertilization processes. So profoundly important. Obviously, we've got big issues as far as the oceans from its impacts, whether it's coral bleaching, loss of coral reefs, or sea level rise. And so that's another area where we've got to sort of look at. It's again quite exquisite when you go back to Charles Darwin in the 1850s, and he was looking at these coral reefs. And you see, we forget that sea level rose about 12 meters about 7,000 years ago as we came out of the glaciation, right? And ice sheets melted. And so these coral atolls, they all had to grow about 12 meters in height to still be there. Otherwise, they'd be underwater. And so what it really represents is that these coral atolls can actually grow quite rapidly. And what happens is all the calcium carbonate they're made of are actually biologically produced. And it's the seagrasses and the mangroves that are actually producing this calcium carbonate and actually building the coral reefs. So the coral reefs are actually biological processes. And if we can sort of basically understand that, then the question is how much, if we're wise, can we actually help coral reefs and coral atolls and islands regrow and rebuild, and can they do that in sync with sea level rise as they did 8,000 years ago, right? And potentially, so that's again a very big positive that can avoid that disaster. So look, the oceans are critically important because that's where our hydrological climate extremes, those dangerous things that are going to hit us, are going to come from, that 93% of heat. There'll be many, many more. I mean, there's more evaporation because of the heating of the planet. There'll be many, many more extreme, intense storms. And that's why the sponge and resilience and buffering and shelter woods on biosystems are going to be critical. There'll also be large areas of the planet, though, because of the change in hydrology, which will aridify because they won't be getting the monsoonal rains, etc., as we talked about earlier. As far as desalination, I mean, again, this is a bit of a furphy. I mean, obviously the oceans are desalinating all the time because as water evaporates from the oceans into the atmosphere, it's leaving the salt behind. So there's nature's desalinization process, right? the amount of desalination that we could possibly do through reverse osmosis is minuscule, and the energy input cost of it is so horrific that it's totally non-viable. And so sure, in some Persian Gulf countries and stuff like that, Israel, etc., where we can say, yeah, we're going to spend this fossil fuel energy to create desalinated water to do irrigation, and at a micro level it's feasible, but only at a massive externalized energy cost. If you looked at the real cost of that fossil fuel energy to do that desalination, it's not viable. And the answer is we don't need it, as we've already talked about, because the ocean is going to be desalinating enough naturally, and all we have to do is harvest some of that desalinated water that's flowing across all the world's deserts in the air anyway. We've got these rivers of fresh water in the air, so we don't need to desalinate them ourselves. All we need to do is harvest them. We don't even have to pay for piping and transporting it. It's all being transported free through the air. We just need to harvest it where we want it through smart ecological management. So what I'm getting at is, yes, desalination will be important in some scientific or very specific affluent societies with plenty of energy to waste, but overall, globally, it's not a significant factor.
So Walter, as the trees call in the rain, many of these questions are really individuals through to, for example, there's a powerful community organization in Los Angeles wanting to call in the knowledge of how to regenerate the carbon sponge. What's the one message you'd offer them as to encourage them to have the courage to take the lessons you've offered out of the session today to move forward with more confidence?
Right. Look, yeah, this is important. The first thing is actually sort of accepting, yes, we need to change, right? And then you localize that stuff, right? I mean, take California. How do we rehydrate California? You know, what's happening in California, very serious, whether it's fire or the acidification of the Central Valley or whatever, the loss of their groundwater. So how do they rehydrate California? What are the options? What are the processes? And at that local level, discuss that. It all comes back to then, yep, okay, how do I rebuild healthy biosystems, sponges, 365-day green, shelter woods, etc. And yeah, then there's plenty of source materials of the how-to of doing that. Obviously, they have to then be translated and tailored to those local situations. And yeah, that's, as we've been talking about, whether it's ecological grazing management, whether it's, you know, agroforestry, whether it's urban forestry or urban agriculture or what. So that's tailor-made. The biggest, I suppose, social barrier is, yeah, getting together at a community group level to say, yes, we have a problem, but yes, we also have the capability, the means, we are responsible and responsible. Here are the tools. It's fair comment to say, and it's a criticism of us, that yeah, we don't have the money, the resources to have this massive publication, and certainly we get not hammered. I mean, it's just puerile, but obviously we get a lot of criticism. Where is this in the peer-reviewed academic literature? Well, it's never been funded, therefore it's not in the literature, but that doesn't mean it's not reality, right? And so that's the next step. Then where do you go? And I suppose it's going to websites and you know, these webinar groups like this one, like holistic management, and just going and just, I mean, like if you look at my name and just Google my name, and here's YouTube's and what have you. And in a sense, you have to get these primary source materials from these primary sources. They won't be in those secondary, tertiary, peer-reviewed journals, but they're 10 years out of date anyway, because that's just reporting things from the rear vision mirror effectively. It's not taking where are the innovative leaders now. There's always 10, 20 years gap between what the innovators are doing and before it becomes, in a sense, documented in the academic status quo literature.